now a little bit bigger. It can be bigger because we have this additional vector, right? So with this vector and a choice of these vectors, we try to satisfy condition 2. And if we can't, of course, now if we have q vectors, we need to see, taking each of the q vectors individually, we need to see if both condition 1 and 2 can be satisfied. Suppose we can't. Of course, then we take 2 of those vectors together. So there are many combinations now. Q choose 2 combinations. If there are q vectors in here, there are q choose 2 combinations. And notice that now the set of vectors that you can choose from here has got bigger now, because we got more vectors. And we continue this process. Sometimes when you add vectors, that space may not increase. See, I've added a few more, and that hasn't increased, but that's fine. We will know if it increases or not. And then we keep doing that until we find one. And when we find one, we know we found the minimum. And if we do all that and we can't find a vector that satisfies condition 1 and 2, then we can declare the triple is not a functional observer. If we do, we can declare it's functional observer and also give the metric cell that satisfies condition 1 and 2. So that is important. Not only we need to know a system is functional observer, but we also need to know what L, because without L, we are helpless. We need to know what L satisfies the 2 conditions. So that's essentially outlining the method. So the paper will have a theorem, if and only if condition, which says this triple is functional observable if L beta and U beta is the space that was inside CSC, right? Inside CSC. So if it satisfies for that, or if it satisfies for that, this is talking about phase 3 observer. Right? It's talking about phase 3 observer where, see, U is the space, is a subspace of CSC. This psi is the additional vectors that we had to increase in the outer boundaries, so that the rank of the condition 1 also increases. So this binomial coefficient here is there because, remember, I talked about the choices, you know, Q choose 2 or Q choose 3. So, so we can, given a triple ACL node, we can for sure, you know, compute these auxiliary matrices, right, and determine if the triple is functional observable or not. And the last theorem is, well, if we have a phase 1 observer, then L beta is the minimum dimension matrix that satisfies condition 1 and 2. And the order of the observer is simply the number of rows in that. If the phase 1 observer doesn't exist, then phase 2 observer we try. If that's the case, well, that is the minimum dimension matrix L that satisfies the 2 conditions. So, I mean, these terms are clearly defined, well defined. And if phase 1 or 2 doesn't exist, then we look for phase 3 observer, which is that, and the rows in that will give you the minimum order for the observer. So that's the final theorem. So example of phase 1 observer. Here we have a 9th order observer. We have a 9th order system. We want to estimate 3 functions, so we have 3 rows. We find that condition 1 is not satisfied, so if I choose L equal to L naught, condition 1 is not satisfied. So you need to add 2 rows here, 2 additional rows in order to satisfy condition 1. And that L beta also satisfies condition 2. Because we can check the satisfaction of condition 2, that's quite easy to do. And then we get that that's a phase 1 observer. So So the order of the observer for this 9th order system, which wants to estimate 3 functions, is a 5th order observer. And here is an example, second example, where it's a phase 2 observer, again a 9th order observer, 9th order system. We want to estimate just one linear function, just this one. And in this case, we find L naught, L equal to L naught already satisfies condition 1. So L beta is L naught, minimum dimension matrix L that satisfies condition 1 is L naught. However, we note that L equal to L beta does not satisfy condition 2, so we need to proceed to phase 2. And if you add this row from CAC, so this belongs to CAC, if you add that row, then condition 1 and 2 both are satisfied. So that's a phase 2 observer. So notice that this is a 9th order system. We design a 2nd order observer here. Right? This is a phase 3 observer. Here is a system. How many? 1, 2, 3, 4, 5, 6, 7, 8. Notice that this is not observable because there is a 0 here. And there's a 5 there. So the system is not observable. But we want to estimate this function here, which is L naught, right? We find that in order to satisfy condition 1, we need to add 3 rows.